Good, good morning, everyone. Let me begin by thanking the organizer for presenting our work. The title of my talk is Pulsation in Spherical Membrane, Role of Active Fluctuation. By membrane, I mean cell membrane, which is made up of lipid bilayers, but not merely that. On top of the membrane, there are protein complexes which diffuse, and when aggregate, they modify the membrane locally, modify the curvature locally to make it concave or convex. Not only that, they can recruit also some other kind of proteins which act as the activator for actin polymerization. Actin polymerization is the first active process which gives the membrane an outward push. Beneath the membrane, there exists an actomyosin cortex from which second kind of activity comes, and when the actin filament growing from the top of the membrane surface comes in contact with the actomyosin cortex, the myosin motor starts pulling it. Active myosin motor starts pulling it, giving them inward curvature, making them locally inward. But studying cell membrane as a whole is difficult one. So what people do, they study giant unilamellar vesicle into which the cellular actins actin filaments are trapped just like this. This is a giant unilamellar vesicle inside, and the green fluorescently labeled greens are the actin cortex. And on the right hand side, this is the theoretical result, the spherical topological sphere, on top of it patterns. Not merely that, when we add active processes and the curvature inducing proteins, they can show the topological sphere. This pattern formations can be can go to pulsation. So the question is, how do we model such system? As I have pointed out, membrane is a lipid bilayer, and on top of it the proteins are diffusing, making them either outward or inward. Here I have specifically put some kind of proteins which make them bulge outward. Inside there is actin cortex, and when the actin filaments starts growing from this surface or the active actin activators and comes to the actomyosin cortex, they give an inward pull. Now how do we define? So we define the deformation as U, and the whole and undeformed sphere with radius R0. U is small. So the variables. First, the deformation of the membrane is U. The protein density we call psi, and inside the actomyosin density to be phi. The outward reaction force due to polymerization is Fr, and the pull by the myosin motors are Fp. So first we write down the energetics for the membrane, such as bending, stretching, and then on top of it we add active processes, write down. So with the dissipative dynamics we come to the equation of motions. So first the bending energy, if the R0 is the R0 is the spontaneous curvature, then the bending energy with bending modulus kappa is this, and there is the osmotic pressure, so the water coming in or going out from the membrane that lead to the volume energy contribution that is given by a pi. Pi is capital Pi is the osmotic pressure, and there is stretching. If you stretch the membrane, that leads to an extra area A, and the stretching energy is this. Now, if we start with an aggregate of protein, and they try, the energetics will be that they will diffuse to come to a uniform density configuration, and if the uniform density is psi 0, then this is the contribution we have to write. But now we have to incorporate the membrane induced curvature due to the membrane bound proteins. The proteins, when we define the coupling as H bar. H bar is when H bar is greater than 0, that makes the membrane bulge in, and when H bar is less than 0, then the membrane bulges out, and the contribution comes here. Note the presence of kappa. So and psi is the protein density. So in this form we write down. So these are the energetics of the passive processes. Now let us come to the active process. So there is active push, and we call it A. There is active pull, we call A star, and to write it, we put, so the active force is coming from the pull, that is proportional to the protein density on the membrane surface, and the pull mediated by the actin filament from the myosin motors is given by this delta function. These are the equation of motion. First one is for the membrane deformation, second one is for the protein density, and third one is for the actomyosin. So with on and off rates, and this is the diffusion term for the proteins, and this is the curvature coupling, and first are the deformation energies. Here you can also note the curvature coupling, and we transform it into L's. We write in terms of spherical harmonics. So note, this is set of linear equations but coupled. We use here linear stability analysis on top of it to predict the possible phases. So as is a 3-variable problem, the eigenvalue equation will be cubic equation, and C controls the stability. If C becomes negative, then you have at least one positive eigenvalue. And you note, if we plot with L, that means harmonics, only some of them are unstable. So that instability will lead to pattern formation, and C equal to 0 will be the phase boundary. So here all the modes are unstable. So only we have to consider up to some mode. Here it is 14, up to 14th mode are unstable, and the rest, as we note, so this is a phase diagram with pull in x-axis and surface tension in y-axis. So surface with higher surface tension we have stable, and this is the deformation coming from instability. Similarly, this is but this is oscillatory mode, and for the oscillation the controlling thing is C minus AB. Again we have plotted this and see that only few modes are unstable. That leads to the pulsation, oscillatory pulsation. I have only chosen L equal to 3 mode, that is some point from here. So in this part only L equal to 3 is unstable, here L equal to 2 unstable, here both L2, 3 unstable, here all 2, 3, 4 are unstable. So to conclude, We have modeled a giant unilamellar vesicle considering both active and passive membrane deformation, observed linearly stable spiral, unstable spiral that leads to this pattern form, unstable pattern formation, L equal to 2 mode. I have plotted. And if we plot chymographs for that, the deformation and the protein density, then we have localized pulsation as well as directed current running pulsation on top of the membrane. With that, I thank my collaborators, Dr. Subhadip Ghosh and Dr. Devashish Chaudhary.
Oh, one question.
I missed something crucial. You have a cubic eigenvalue equation. You have 3 variables, that means. I didn't understand the third. One is membrane displacement. One is your protein concentration. What is the third one? I just missed.
Third one is the actomyosin density. Which
I see, actomyosin density. I see. Thanks.
We could take another. There is.
Curvature, no, it's a coupling actually. When it bends, so it's whatever it can take. I mean, 2 by R0 is the spontaneous curvature. Then there is a coupling. So with that, whatever curvature it takes.
So according to you, what is the definition of curvature here? I mean, you are relating the stress energy with the curvature, right?
Right. So, mean, yes, I'm talking about mean curvature here. Mean curvature of the membrane.
Okay.
Yes. Thank you.
Let's thank the speaker again.